Okay, we can consider it like this. Can one of you tell me what kind of mass distribution a solid hemisphere is?
Volumetric.
Volumetric. The entire volume is filled with mass. Okay, it's a volumetric mass distribution. Assume its radius is r, mass is m. What is the formula for volume of a full sphere? Volume of a full sphere.
So 4 by 3 pi r cube.
4 by 3 pi r cube. So for a hemisphere, it will be 2 by 3 pi r cube. Okay. We have to find out the position of center of mass. Does this system have a line of symmetry? Yes, it does. Same thing. The vertical line passing through the center of the base. That is a line of symmetry. We'll treat it as the y-axis and we'll treat this horizontal line as the x-axis. Fine. Since we identified a line of symmetry, we know the center of mass lies on the line of symmetry. Therefore, all we need is the y-coordinate of center of mass. Okay. And the formula for y-coordinate of center of mass, as usual, integral y dm divided by integral dm, because this is a continuous mass distribution. Again, as usual, we have to visualize the mass present at a particular y-coordinate. Okay, just a moment. Okay, you all imagine, like if you look from the side, it will look like a semicircle only. Exactly from the side, if you see, it looks like a semicircle. I'll use that semicircle image diagram. Fine, tell me, if we consider a particular height, okay, let's say a particular y coordinate till here, and visualize a small change in the y coordinate. Okay, all the mass enclosed in this region is what we call as dm. The width of that region or the height of that region is what we call dy. Okay, you can visualize it in the solid sphere also, solid hemisphere also. So if you chop it horizontally, what is the shape of the element that you get? What is the shape of dm?
Circle, sir.
Circle. Okay, we call it a disk. Okay, see, circle is only the boundary. Disk is the entire area. Okay, so you should call it as disk. Are you all able to visualize this? If you chop an onion horizontally, what comes out is a disk, and that disk is a collection of rings, onion rings. Okay, let me just show you the visualization. It will be okay, fine. I'm not able to find an image. Okay, it's somewhat like this. Fine. What you get are disks when you cut a sphere horizontally, or along a certain plane. If you cut it, you get disks like this. Okay, if you visualize the disk element, just a moment, this kind of visualization is important, as I said. So, Okay, you won't be able to see that at all. The disk element has slant edges like this, and this is what it looks like. This whole region is filled with mass. Okay, Yusuf, is this clear? Are you able to visualize the chopped part like this? Rishi, is this clear?
Yes, sir.
Pawan, what about you?
Yes, sir.
Okay. And if you look at it exactly from the side, this is what it looks like. Slant length, slant length. This vertical height is dy, slant length is dl. Now the whole thing is filled with mass. Okay. Again, the usual drill that we do, we need to express dm in terms of dy. And whenever you need to express the mass of an element, you need to consider what kind of mass distribution it is. And we already discussed that it's a volumetric mass distribution. Now listen, for volumetric distributions, we use the general formula for density. The general formula for density, okay, denoted by the symbol rho, okay, is mass by volume. And since this is a uniform mass distribution, total mass by total volume will be equal to small mass by small volume, dm by dv. Therefore, dm, the mass present at that y coordinate, which is the mass of that chopped piece, okay, the disk that we got, will be density into volume of the disk. How do we write volume of a disk? We write it as this area multiplied with this height. But you may ask, sir, if you do area into height, won't we be getting only this much volume, like a cylinder? Yes, you will be getting only that much volume. You will be missing out on some volume on the sides. But if the height is negligible, no, dy tends to 0, the volume you are missing out on the sides will also be negligible. Okay, compared to this cylinder volume. Okay, so what we are going to do is we will write dv, the volume, as the area of the disk that we got multiplied with the height of the disk dy. Okay, so it seems to be a little easy to express dv in terms of dy, and if you can do that, if you can express dv in terms of dy, you can get dm in terms of dy and you can integrate. But you still have to derive an expression for that area of the disk. Area of the disk obviously is a circle, okay? The boundary is a circle. Its area will be pi r square. But what is the radius of that disk? The radius of that disk is x, which varies from disk to disk. Okay, when you chop that hemisphere like this, the disks that you get will have different radii. Okay, let's call it as x. Then its area becomes pi into x square, circle's area. But this again leads to a complication. The volume is now pi x square multiplied with dy, where x is a variable. We don't want two variables, we want only one variable. So what you now need to do is you need to relate x and y. Can any of you quickly recollect and tell me how x and y are related? Y is that vertical height, x is that horizontal distance.
Square Pythagoras theorem. R square is equal
Pythagoras
to x
theorem.
square.
Good. R square is equal to x square plus y square. If you do that, you get r square. Okay, you get x square as r square minus y square. No square root or anything is needed. Therefore, the volume dv, which is the volume of the thick disk that we got, becomes pi into x square is nothing but r square plus y square. Okay, multiply with the thickness dy. Now we have the volume entirely in terms of y, which is a good thing. We can now express dm as density into volume. Mass of the element is density into volume of the element. Volume of the element is pi into r square minus y square dy. Okay, we got mass in terms of dy and y is the only variable. So this integration is a little easy. We don't have to take help of some other variable and all. Therefore, we are now in a position to derive the y coordinate of center of mass. Integral y dm divided by integral dm. Integral dm will be the total mass. Okay. So 1 by m integral y dm. Y into dm is this whole thing. Density multiplied with, okay, wait. Multiplied with pi multiplied with r square minus y square dy. We'll split this into two integrals because there's a minus sign in between. So first integral becomes 1 by m into integration of y rho pi r square dy. That is one integral. The other integral will be 1 by m into integration of y rho pi y square dy. Okay, there's a minus sign in between, not plus. Minus. Okay. Now rho pi are constants. We can put them aside. R square is also a constant. Y is the only variable. So the first integral becomes, okay, from both integrals, I'm taking rho pi divided by m constant. In the first integral, what will be left? R square stays outside, integral y dy. And in the second integral, rho pi and m have gone. Y into y square is y cube. You are left with integral y cube dy. These are not even difficult to integrate. Okay, so this derivation is kind of simple. But one mistake anywhere and the whole result will go wrong. So you need to be careful. R square into, what is integral y dy? Any one of you?
Y square by
Y square by 2. Good. We still have to substitute limits. What is integral y cube dy?
y to the power 4 by 4.
Y power 4 by 4. Okay. Y is the height of the disk that we have taken. To cover all the disks of this hemisphere, what are the limits of y? What is the starting value? For the bottommost disk, how much is y? And for the topmost disk, how much is y? Aishwarya, what will be the limits for y?
0 and
0 and?
R, sir, radius.
Okay. The last disk will be at the height r. Correct. 0 and r. So those are the limits that we are going to substitute, 0 to r in both the integrals. So what does it become? Density into pi divided by mass into r square. When you put r here, you'll get another r square by 2. So this thing becomes r power 4 by 2. When you put 0, it is 0. So no need to bother about that. Minus r power 4 by 4. Again, when you put 0 in the second integral also, it is 0. Need not bother about that. R power 4 by 2 minus r power 4 by 4 is r power 4 by 4. Therefore, it becomes density into pi divided by mass into r power 4 divided by 4. Now what is density? Total mass by total volume. So in place of density, I'll write total mass divided by total volume is 4 by 3. Okay, not 4 by 3, 2 by 3 pi r cube. This is a hemisphere. Pi r cube. So cancel whatever you can. Pi gets cancelled. R power 4 r cube, 1 r will remain. Mass gets cancelled. So pi is gone, mass is gone. 4 2s is 8. What will you be left with? 3 goes to the numerator. 3r by 8. That is the y coordinate of center of mass of a solid hemisphere. Three r by 8 is less than r by 2. Okay. So it will be at a height less than half of the radius. Half of the radius is maybe somewhere here. Center of mass will be here. 3r by 8. Okay, let's go through the derivation once again. It's a volumetric mass distribution. Continuous mass distribution has a line of symmetry, which is the y-axis. Therefore, we need the y-coordinate of center of mass, which is integral ydm divided by integral dm. As usual, we first visualize the mass that is present at a height y. In this case, at a particular height y, if you take the mass, it will be in the shape of a disk. Okay, the disk has a thickness dy and it has some area of its own, which varies from disk to disk. Okay. What we now need is the mass present in that disk. And for that, we thought of what kind of mass distribution it is. It's a volumetric mass distribution. So we need the volume of that disk. Disk is like a cylinder, of course, with slant edges, but we consider it as straight edges. The volume we are missing out is negligible. Okay. So dV, the volume becomes area of that disk multiplied with its height dy. And we did all that. We were able to directly get it in terms of y, and easily we integrated, substituted limits. Okay. The y coordinate of center of mass came out to be 3r by 8. So what we did is kind of like this. Just a moment. We considered the hollow hemisphere. Okay, not hollow hemisphere, solid hemisphere as a collection of disks like this. Okay, each disk has its own radius. Bottommost disk has a large radius. Next disk has a slightly smaller radius. Third disk has even smaller radius, and so on. There are infinite such disks. Now, this is one idea. We can treat it as a collection of disks and solve. That's fine. Can any of you tell me any other way to derive the position of center of mass of this solid hemisphere? Can we treat it as a collection of something else, some other shapes? Can we treat it as a collection of some other shapes? Whose center of mass we already know. It can be done. You can treat it as a collection of hemispherical shells, hollow hemispheres, like bowls placed one on top of another. Balls of varying radius, not balls of the same size. Okay, one small ball, next a slightly bigger ball, then a slightly bigger ball, even bigger ball, and so on. Now, I don't have the exact diagram for a hemisphere, but I have it for a sphere. You can treat it as a collection of layers like this. Okay, here it's a sphere whose layers are shown to you. You can treat a hemisphere also as a collection of layers like this. And the base looks like this. Fine. So there are many shells, hemispherical shells, which form the overall hemisphere. Okay. Now, what's the benefit of taking it like this? What's the benefit of taking it as a collection of shells? See, if you derive, you will get the same result. That's fine. But we should be prepared to solve a problem of any kind. Now, in this case, like the result that we have derived now, we assumed it's a uniform solid hemisphere, means all particles are identical. But it's quite possible that they give you a hemisphere like this, where one layer has one density like this, another layer has a different density, different kind of particles. So density varies from radius to radius. Then you will have to treat it as a collection of shells like this. You have no other choice. Okay. So in cases of variable density, you will have to treat it like this. It's also possible that the density varies height-wise. Then you will have to treat it like this. Okay. The bottommost particles have one density. The next layer of particles have a different density. The third layer of particles have a different density. If density varies height-wise, you will have to chop it height-wise like this. If density varies radius-wise, then you will have to take it as a collection of shells like this. Okay. So if you visualize how you need to solve it is, just a moment. Why am I not able to select the semicircle? Okay. So assume this is the boundary of the hollow hemispheres, not hollow, sorry, solid hemisphere that is given to you. What you now need to do is treat it as a collection of shells like this. Okay, thick shells. And the given solid hemisphere is a collection of many shells like this. Now this thick shell will have some mass inside it. Okay, it's a hemispherical shell. Its mass is what you take as dm. And the overall solid hemisphere is a collection of shells like this, bowls like this. Okay. Now, for this bowl, the radius can be assumed to be small r. And you can take the thickness as dr. And for, if you consider all the bowls, r varies from 0 to capital R. Because for the first smallest bowl, the radius will be tending to 0. And for the last bowl, the radius is the radius of the given solid hemisphere itself. So the range of small r will be from 0 to capital R. Let it be. We are treating it as a collection of shells like this. Each shell has its center of mass at exactly half of its radius, r by 2. We derived that today itself. For a bowl, open bowl, the center of mass is at a height r by 2. For a closed bowl, it is r by 3. For open bowl, it is r by 2. So all this mass dm is present at that height r by 2. Therefore, if you want to find out the y coordinate of center of mass this way, you'll need to do integral y dm divided by integral dm. No? This mass dm, this shell of mass dm, you can assume it is present at a height r by 2 divided by integral dm. Integral dm is the total mass. Okay. But again, to integrate this, you need dm in terms of dr. Dr is nothing but the thickness of that shell. How do you write dm in terms of dr? Think of the mass distribution first. It's a volumetric mass distribution. So density is equal to mass by volume. So dm becomes rho, that is the density multiplied with the volume. Okay. How do you find out this volume? The shaded volume is nothing but volume of the outer hemisphere, which I am drawing in yellow. You can consider a hemisphere like this. And from that, you have to remove the volume of the inner hemisphere. If you do that, you will get the shaded volume. Outer hemisphere has a radius of r plus dr. Inner hemisphere has a radius of r. You can easily write their volumes and subtract. Okay, but Yesterday, when we derived the position of center of mass, yesterday or last class, of a semicircular disk, think of what we did. We considered the semicircular disk as a collection of rings, thick rings or wide rings. The shaded area is the area occupied by that ring. How did we find out that area? We did outer semicircles area minus inner semicircles area. But what was the approximated result? Length multiplied with the thickness is the shaded area if the thickness is very small. Okay. Actually, you are supposed to do outer semicircle minus inner semicircle, but it turns out to be equal to this length multiplied with this thickness. We can use the same idea here also. What we are looking for is that volume. You have to do outer hemisphere's volume minus inner hemisphere's volume. But since the thickness is very small, what is the thickness? dr. That's the thickness of that shell. Since it is very small, you can do it as volume is area multiplied with the thickness. Okay. Therefore, dV will be taken as, how much is its area? It's a hemisphere. So 2 pi r square is its area. And what is its thickness? dr. Therefore, dm becomes density into 2 pi r square dr. We got dm in terms of dr. Once you get dm in terms of dr, you will be able to integrate this and tell where the center of mass is. Let us do that quickly. Therefore, y coordinate of center of mass is integral. Y is r by 2 and dm is density into 2 pi r square dr divided by integral dm is the total mass m. Okay, cancel whatever you can. Density and pi come out. Density pi divided by mass integral r cube dr, and integral r cube dr is r power 4 by 4. Substitute limit 0 to capital R, it will become capital R power 4 by 4. And if you see, the final result seems to be the same that we got before. Density into pi by m into r power 4 by 4. We got the same thing here also. Density into pi by m, r power 4 by 4. Therefore, the result will again be 3r by 8. But this is a different approach, treating the solid hemisphere as a collection of shells. Okay, so these are the derivations that you need to know how to do. This is basically, these derivations teach you how to take the element, how to express the mass of the element. And I told you, this is a general approach in science. You first learn the behavior of particles, you extend the behavior of particles to systems, and this is how you do that. Fine. So today is what, Friday? Fine. Tomorrow you won't have a class. Sunday also, mostly we won't have, Monday only. But I will be sending you a worksheet, and along with the worksheet, you will have to practice all these derivations. In each case, how did we visualize the element? How did we express mass of the element? How did we substitute it in the integral and get the result? You should be thorough with this. Because as I said, in this chapter itself, the next concept we are going to discuss is something called moment of inertia. We'll solve some problems about center of mass. Then we'll move on to moment of inertia. Basically, it is nothing but rotational inertia of a system. And there also, we'll first derive an expression for rotational inertia of a single particle, and we'll extend that to different systems, where you will be again taking mass elements like this and integrating. Okay. So make sure you are very confident in these derivations. If you have any doubts, you can call and ask, or you send it on WhatsApp. I will help you out. And the last worksheet, I got answers from only one of you. Others, sit and solve that worksheet. Tomorrow or day after tomorrow, you'll get another one. You have to solve that also. It will be based on these derivations. And as I said, I may give you systems whose density varies height wise. I may give you systems whose density varies radius wise. Okay, fine. So whenever you find time, tomorrow, day after tomorrow, solve the worksheets and send them to me. See, it is for your improvement only. I'll get to know how much you understood, what you did not understand. Okay. Fine. We'll stop it here. It's been too long. Thank you all. We'll continue in the next class.
Thank you, sir.
Thank